my major research topics here. Before we start directly with the presentation, I'd like to acknowledge everybody who has been involved in that research fields, especially my boss, Gerhard Stock, with who together I developed a method which is called dissipation-corrected targeted molecular dynamic simulations, which I'm going to talk about a bit in a moment. And then a range of very talented PhD students, so Benjamin, Matthias, Simon, and Miriam, and some bachelor and master students, so in this case, Victor, Marie, Zoe, and Fabian, who all worked on different aspects of the project that I'm going to talk about now. And you will see their names coming up or the pictures as soon as I talk about something which is related to their work or which they worked on. Now, before we go directly into the scientific part and the details of condensed matter physics, I'd like to give you a general overview. What is the interest of this field of scientific problems that I want to tackle, which is to come up with an improved way of designing drugs. So here you see a normal timeline for the development of drug compounds. And what you can see, it starts small on the left side from identifying a protein where we would like to inhibit or activate to obtain some reaction in the body, until on the right side, then really to be able to sell a drug. And this process can take something like up on the order of 10 years. And is usually involved with costs on the range of several tens of millions of euros or US dollars. And what you see on the bottom is then the rate of or the percentage of attrition in each step. And what we're going to see here on the very right side now this number here. That most of the drugs actually fail very late in the process, where this is very expensive because a lot of investment has been done beforehand. And these last phases where the drug is applied to candidates in a clinical environment is very expensive as well. So that means drug campaigns often fail very late and when a lot of money has been invested already. So what are the reasons for this? So one of the reasons is that, we just delete this here quickly. So, moment. One of the reasons is that drug development is mostly focusing on equilibrium properties of a drug. Because they are well understandable. For example, here the difference in the free energy on the left between a bound and an unbound state can be directly translated in this KD constant here, the dissociation constant, which is one of the major properties which is evaluated or optimized during drug development. And this picture is completely fine if you assume that you take a pill and it gets into your system and then is taken up into your bloodstream and is then diffusing to where it should act in the body. The major problem here is that this is good as long as you will still treat everything under equilibrium. However, our body is not in equilibrium state. So our kidneys and our liver are directly eliminating any kind of drug which is in our bloodstream. So that means even if you have here on the left side this picture of a distribution between a bound and an unbound state in the free energy, these unbound and bound states exchange with a certain rate. And in case that the exchange is very quick, then this unbound state is going to be eliminated more and more by our organs. And so the population from the bound state is just flowing back there to the unbound state. And so even in case that you have a very tightly binding drug, after a while, you have simply no population of this compound in your body anymore. And the possibilities, what you can do then, if this is happening, is either you apply a drug each 3 hours, which is very impractical overnight, or you give that in a clinic via an IV, which is again not very practical in a general way. Or you just increase the concentration in the body. And as soon as you increase the concentration in the body, binding will happen in other places as well on the body, and this will cause then side effects. And most drugs then are eliminated because the side effects are just too strong. What could we do about this? It turns out if we do not focus on designing a drug which is binding very tightly, but which takes a lot of time in the bound state, you can have the situation where the unbound state is pretty much eliminated in the body, but the compound stayed at their bound state. And so with this, you just need to apply a drug maybe once or twice per day, and you do hardly have any off-site binding and therefore no side effect, and that drug is way better in this case. Now, this of course requires us not to focus on being able to calculate now free energy differences, for which there are a lot of different methods, but we need to obtain information about the time course or the time scales of that binding and especially of the unbinding. And this is a huge problem for MD simulations because molecular dynamic simulations are limited so by physics, so that we need to induce a time step for the numerical solution of Newton's equations of motion. And this time step needs to be slower than the fastest motion in the system. The fastest motion in such an atomic system is an bond vibration, which is on the order of several tens of femtoseconds. That means our time step needs to be on the order of 10 femtoseconds, of 1 or 2 femtoseconds. So 10 to the power of 15 seconds. So if we would want to simulate a simple second, we would need to perform already 10 to the power of 15 iterations. And this is hardly be doable on current computational hardware. The fastest currently available computer, so Anton 3 in New York in the D.E. Shaw Research Labs, can perform 100 microseconds per day. This is a vast improvement over everything that we can do with other architecture. But even with this architecture, we would require 33 years for only calculating 1 single second. So this is very unfeasible to perform these kinds of simulations for investigating drug unbinding. So if we cannot work with now numerical simulations by solving atomistic simulations, can we somehow induce or use smart physics in a way of creating reduced models? And this is the approach that we take here, which is that we go away from a fully atomistic picture, and instead of calculating simulating atoms, we use these kind of simulations to parameterize an efficient model, in this case, a free energy landscape, along a coordinate of interest in our simulations. For example, that would be the distance between the center of mass of a protein and a bound drug. And because we're pretty much only interested in the time course of how far the ligand is away from its bound state. And if we are just interested in the dynamics along this reduced moment, there's background noise. I will just close my okay, now I've got closed my speakers just in case if you want to say something, please raise a hand here in the chat. So the trajectories are that, so we use this reduced picture of arrangement dynamics on the left side, where we predict then dynamics along this distance coordinate based on a free energy drift term minus a friction term plus a fluctuation term here, where we have a fluctuation amplitude which is coupled to the friction coefficient, and then we employ white noise fluctuations to just represent all the dynamics of the surrounding system. If we have that, integrating numerically this kind of equation is way more efficient computationally than the fully atomistic simulations. And of course, what we then need is we need to find a way how to parameterize the free energy on one hand. which again, for this exists a lot of different methods, but we need to find a way how we can parameterize this friction profile here as well. And just to give a very quick overview about what this friction term is. Um, Now, friction, of course, if you are familiar with from everyday situations, but what is that in the framework of an atomistic simulation? Now, um, to give you a better overview of this what we want to use this friction term for. Here you see on the left side a simulation where I have a red van der Waals sphere and I just throw that in another bunch of blue van der Waals spheres and just let it collide there with the remainder of them. And this is now a fully atomistic simulation. And I'm now going to show you the same picture on the right here. It's exactly the same simulation, but I'm going to remove the blue particles. And what you will see is, in this case, you see that the red particle only in the beginning slows down and then in the end starts to wiggle apparently chaotically or randomly. And so we do not see the blue particles, but we need to somehow represent these kind of dynamics. And we do this now with this combination of a friction factor and a fluctuation, where the fluctuation is based on the connected to the friction as well, because the source of the friction and the fluctuations are both then degrees of freedom, which we have integrated out to obtain our free energy landscape. And if we then perform a long-run simulation, here on the top right, there, you see as well that the numerical integration of a long-run integration for representing such a motion looks very similar. So this particle is accelerating sometimes in directions randomly and then is slowed down again by its surrounding. So as a take-home message in this case, so free energy from our profiles gives us the mean force between the ligand and the protein. And the friction is then there for obtaining the fluctuations of this mean force around its mean by means of the respective variance in the friction. So in case that we have both these properties, so the free energy along this distance coordinate and the friction factor along the distance coordinate, we can reproduce some dynamics which are very similar to the all-atom dynamics, but we still need a method how to calculate both. And we do this by an approach that we again call dissipation-corrected targeted molecular dynamics simulations. And so for this, we start with fully atomistic simulations where we enforce the unbinding of a ligand from its bound state via a constant velocity constraint. This constant velocity constraint is employed by force, which the constraint applies to ensure this continuous velocity motion. And if we integrate this force over this pulling distance, we end up with a work that we need to pull out the ligand. However, this work, of course, is under these conditions larger than the free energy for the same process, because we do this within a finite time, because it's a non-equilibrium simulation. Now, to obtain the free energy from this non-equilibrium work, we can employ Jasinski's equality. However, Jasinski's equality here in its pure form is numerically really inefficient, because this mean of an exponential decays very badly. So instead of this, we perform a cumulant expansion of the logarithm until second order. And where we then have an equality between the free energy, the mean work that we need to employ in an ensemble of a lot of simulations, and some additional term which is dependent on the variance of the work. So just from looking at this, this variance needs to represent something which is the work that we need to apply in addition to the free energy to pull out the ligand in a non-equilibrium setup of simulations. Now, if we now want to interpret this kind of simulations in the framework of a Langevin equation that we want to employ later for performing simulations, we could say as well that well, the kinds of same kinds of dynamics should be able should be we should be able to simulate the same kind of dynamics um, from these pulling simulations in the framework of this Markovian Langevin equation, and then this pseudo force from or the constraint force would be added to all the other forces which are appearing in the system. And it would simply negate all the forces because then we have a situation where the ligand is not accelerated anymore, and no acceleration means constant velocity, which we preset with the constraint. Now, if we perform a mean over a lot of simulations and then integrate along the respective coordinate x, then first of all, the mean will drop out the fluctuations here because they have a zero mean. And all the other terms, when we rearrange them, will appear in this shape here on the right side. Now, if we compare the right side equation now with the one in the middle here from Jasinski's equality, we can identify that there is a possibility to calculate a friction factor directly out of these non-equilibrium simulations, which is corresponding to the first derivative of the work variance in the ensemble of simulations with respect to the position along this unbinding distance x. And so with this, we have a way how we, from an ensemble of non-equilibrium unbinding simulations, can directly calculate a free energy of unbinding as well as a friction factor of unbinding. Of course, then we need to assume that the friction is close enough to the friction under equilibrium conditions. We ensure this by short or slow pulling. And with this friction factor and the free energy, we can then perform these Langevin simulations. Again, they are very fast. So for the calculation of 1 microsecond, we can go up to as well a time scale, a time step of 5 femtoseconds under these conditions. And we can then calculate 1 millisecond within just 20 hours on a standalone PC, which is significantly better than molecular dynamics simulations. However, this is still far away from the seconds or minutes or hour range that we're interested in. However, here we can employ another trick, which is that these fields, they do not change, or we can pretend that they do not change under high temperature. So we simply increase the temperature of simulation, then perform respective dynamics at high temperatures, and then assume that everything, so the binding and unbinding is following a Kramers type kinetics, and then can use Kramers rate law to rescale the high temperature simulations back down to a temperature where we derived the respective friction and free energies, for example, physiologic temperature, and then can predict the respective rates at these temperatures that we are interested in. And with this, we can then even perform or predict rates on the hours of seconds to minutes to hours. So now with showing you how our theory works from the approaches, I want to give you an outlook. How good are we now for the overall benchmarking of our approach? We turned to simulations of a simple ion solution, so one single sodium ion and a chloride ion in water. And there we simulated we performed our calculations here, obtained a very well converged free energy landscape that you see here on the left side, which is corresponding very well to the respective free energy from unbiased simulations. We checked that, and then I calculated our respective rates. And you can see here on the right side that the unbinding and binding kinetics of the Langevin simulations are reproducing the kinetics from fully atomistic molecular dynamic simulations within a factor of 4. Well, here again, factor of 4 sounds large first, but bear in mind we need to check what are the error margins that we're dealing here with. And on one hand, the overall error margin of such a rate is given linearly by the error margin in the friction, but exponentially in the error margin of the kinetics and of the free energy barrier estimate. And usually, the free energy barrier estimate has a mean error on the order of 3 kT. That means already so in case that we have an average error, that would lead to an error of e to the power of 3. And so this is roughly a factor of 16. So in case that we have an error which comes from the friction on the order of a factor of 4, this is negligible against the free energy error. And usually in the field where I'm working in, that currently in the correct estimate within a factor of 10 is already considered a success. The reason why we have this discrepancy between the Lagrangian simulations and the atomistic simulations is most likely that the constraint still induces some changes in the overall dynamics, especially of the water molecules here in the surrounding. And therefore, this appears as an apparent increase in friction. And this is a well understood artifact. So we are always normally overestimating rate. So we are too slow, essentially. So this looks very good, so that we know roughly from our benchmarking systems what are the error ranges. We know the theory, how to employ that. When we had all that settled, I thought, okay, let's go into now real system. Let's perform simulations with real proteins. And there it turned out this did not directly work. So here on the left side, you see one simulation with a protein which is called HSP90 and an unbinding of a ligand there, which I show here on the top in the movie. And the free energy estimated by some equilibrium-based approaches is here given in blue. And our estimate here is with our approach is in red. And you see, first of all, it is completely wrong in the distribution of free energies between the bound state and the unbound state. And this difference is even on the order, secondly, of roughly a covalent bond. So we do something really wrong here. What is that? Now, the problem here is that ligands can unbind in different pathways from binding site. Along different pathways, you have different contacts with the surrounding protein, and that means the friction is going to be different. So even though along the path, so the respective work distributions along one pathway might be Gaussian in the end, if you then just combine all the data about both pathways into one single analysis, you will see the appearance of one double Gaussian. And if we then use our second order cumulant approximation, this is equivalent to assuming that this bimodal distribution is following a single modal Gaussian. So you would assume that the mean is somewhere in the middle and you overestimate the width massively. If you overestimate the width of the Gaussian, that means the variance is overestimated, and this causes an overestimation of the friction, which explains the apparent artifact that we see on the left side. So what can we do with this? Well, we can now collect the trajectories according to the different pathways. And then we perform a Jasinski or cumulant expansion estimate of the free energy along each pathway independently, and then perform MD simulation or Lagrangian simulations along each pathway independently, obtain pathwise rates, and then combine the pathwise rates into one global rate, which should correspond very well to the given experimental rate that can be seen in case one performs an experiment with a real protein as an observable. So when we did that with a 2D test system, we could see that actually, yes, this approach works. So our combined pathwise free energies here on the top are corresponding very well. So just a moment, sorry, I'm just going to show this here. So the pathwise values correspond very well to the 2D unbiased estimates. Only for binding free rates, we have a little offset, which comes just from problems of sampling the full outside of the protein, where we always will perform some mistake and we'll lose some information with just pulling the ligand out of the binding site. Now, just a moment. Okay, so the problem here is this is very well definable for these kind of test systems, but how can we find the respective paths that a ligand is taking out of the binding site? And here we adopted a lot of different approaches from methods that you're usually there for finding states of a protein, like conformational states, metastable states for the construction of Markov state models, and especially dimensionality reduction process methods to find collective variables which describe us the respective pathways. One very simple way is that we can fit the protein structure of all trajectories onto one reference structure and then calculate just simply the time-based mean of the root square mean displacement between the ligand atoms between the different trajectories. However, we found that it's significantly better to obtain a dimensionally reduced overview of these approaches by, first of all, focusing on internal coordinates within such a simulation. That would be minimal distances between any kind of atom in a ligand and any kind of atom in one specific amino acid. Calculating these distances between ligand and an amino acid over time, and then first of all building a covariance matrix between all these distances and then diagonalizing them. So this is then the same like a principal component analysis, which is well understood for equilibrium simulations to find eigenvectors that can be used as reaction coordinates for describing such processes. But here we use this now in the framework of a non-equilibrium system. So we can start with minimal distance contact distances between ligands and proteins, but then calculate their respective dynamics over time, calculate then the respective covariance matrix, diagonalize it, and project then the trajectories into the first few eigenvectors which are of interest. Mostly we can just work here with 3 eigenvectors. And then within this picture of just a moment, of projections, we then calculate the pairwise distances between trajectories of time points and can then use that to calculate overall similarities averaged over time for trajectories. So that means trajectories which are very similar, following very similar patterns here, like the black trajectories on the top right, they are going to have a very high similarity. Whereas the trajectories in black and in red are very dissimilar, very distant, and this is reflected then in a very low similarity. Now, if we have a set of trajectories, we then take this similarity matrix and use machine learning to rearrange the whole similarity matrix into a block diagonal form that you see here on the bottom right by a so-called Leiden clustering with a constant Potts model, which tries to maximize the number of, or the overall sum of similarities within a given within such the matrix and within separate clusters versus and it does that against a reference value of similarities which is just distributed evenly, randomly between these different nodes. And by this algorithm is essentially giving us some suggestion which trajectories are very similar and how many clusters of similarities we have. And we only need to define one single parameter here, in this case, this gamma, to obtain so a very quick and very well understandable or optically very well understandable picture of which trajectories are very similar with each other. So if we do all that now together with a real protein ligand system, how well does that work? So here on the left side, I show you the trypsin benzamidine complex, which is a standard protein that a lot of people in the community of calculating ligand unbinding rates are using. And here we directly observe the appearance of three different pathways. We only need two principal components about this. So the top pathway in orange, the middle pathway in gray, and the bottom pathway in blue. And if we then perform respective Langevin simulations along all these pathways, combine them into the respective rate into one major rate, you see that we pretty much spot on hit the experimental rate. And with the on rate, we are still off by only a factor of 6, which of course then, which again is very good compared to other systems or other approaches that are on the market for this as well. Then in general, how well is this approach applicable over a different range of systems? So for the two other proteins that we investigated, so the HSP90 complex, we obtained a similar accuracy, and here for the streptozidine biotin complex, we even obtained a much better agreement, even with a factor of only 2. We can even use the approach under certain conditions to predict the rates of conformational transitions of, for example, peptides. Here, the alanine D dipeptide, where we simulated the alpha-beta transitions with an accuracy of a factor of 3, and T4 lysozyme, an opening-closing motion that this protein has, we even obtain with an accuracy of 1.5 or of 5 for the system. So we have a very good agreement overall the board. Again, usually what you need to do here is you need to perform a lot of simulations. So that means on the order of 500 simulations, you need to roughly have 100 simulations per pathway to obtain a quite good convergence of free energy. In case you do not want to do that, there's a quick and dirty way of doing the same approach, where you, in case that you just have a library of compounds and you want to see which ones of them are fast and which ones are slow unbinders, you can just simply take the ligand, pull it out of the binding site, check what is the average work that you need at the end to in this ensemble of simulations to pull the ligand out, and then compare these values with each other. And usually this is already is quite good scoring value for obtaining information which of your compounds are slow unbinders and which ones are fast unbinders. With a little caveat here, you can only do this with chemically very similar compounds, because this approach assumes that the friction for all the compounds that you compare is the similar, and for this you need to have chemically quite close structures. So you cannot compare different compound libraries with each other. So while this sounds quite good so far, in the end, I would like to point out that this problem here is then usually now related to finding, so the major problem that we still face here is that we need to find a good reaction coordinate for describing these kinds of these kinds of pathways. And so far we have found that depending on which kind of protein, we have different kinds of pathway collective variables that we need to take into account. For example, when we just recently took a look on a G protein coupled receptor in the unbinding of a ligand, we found that the pathways are defined by ligands either going straight out of a binding site here. In this case, that would be this cluster 4, or going through some place where the ligand is going into the membrane, where we could not resolve any free energy anymore. Second question that one might ask is how well do these these distance measurements that I showed you before are performing over other possibilities to calculate the distances. We just recently checked this and turned out that our Euclidean PCA distances here, DE, are pretty much on par or even superior to more complicated or more elaborate distance as calculating methods. For example, like Procrustes or dynamic time warping approaches. Wasserstein distances are roughly on par with the accuracy, slightly better sometimes, but are calculated so a bit more expensive from the computational side to calculate. And last but not least, we have even sometimes cases where a single hydrogen bond can completely change the overall picture. So this here is one compound of ligands that bound to two compounds that bind to HSP90, which are only differentiating in the detail in the side chain. So in one case, we have a sulfonamide. Here, this is compound number 4. Whereas in compound 3, we have a bridge with a peptide bond. And even though the respective distributions of unbinding paths just statically look very similar, we can only resolve the pathways for one of those two compounds, not for the other one. And it turned out the reason why this was the case is that the compound here with the sulfonamide, that is forming a hydrogen bond within the compound itself. And this hydrogen bond can break upon contact with surrounding water or not. And in case it breaks, then it is behaving differently during unbinding than when it's not breaking. And we just take this the distance between these two groups which is called the corresponding to the hydrogen bond into account as a reaction coordinate. Then again, we can separate the respective free energy path, so the respective pathways, and obtain good assumptions or estimates of free energies of unbinding. So that means that this this pathway separation is really dependent on the chemical system that you are investigating, and it is never given that you can translate the knowledge from one compound series to another. Very last point. Does this approach help us as well for better understanding of friction processes in protein ligand systems as well? Do these kind of changes of or these differences in pathway somehow materialize in some true life properties that the system can have, or differences in friction? And it actually does. In this case, these are results from a collaboration here with Thorsten Hugel at Freiburg and Bijan Balsa, who are experts in atomic force microscopy, where they can pull out ligands from binding sites in proteins, and not only do this with atomic force microscopy in such a way that you pull out ligands straight off of the binding pocket, but by pulling out ligands at an angle from a binding pocket in single molecule experiments. And they were quite surprised when they analyzed the data, because when they pulled out with increasing azimuthal angle, here you see this angle psi here. So they assumed what would happen is that the ligand needs more and more to go across parts of the protein, and so that the barrier for unbinding would increase. And turned out that was not the case. So the barrier stayed pretty much constant for all the different angles, but the friction term, that went up with higher angle. And this is something that they could not understand completely. And so what we did was we started to perform simulations with the same protein, but now starting to pull into different distances, so different angles along out of the binding site. And it turned out that when we made estimates of the friction, or in this case, then the variance of the force that we need to unbind the ligand from the binding site, dependence of the respective angle, we saw that this variance for each unbinding event along given angle combination here, that does not change much. However, if we ignore that the ligand, so that the protein on the surface has a certain orientation and that we cannot fix this, which is the case in the experiment, and we just throw together all these different pathways according to this angle phi, then we see that in this ensemble of trajectories, the variance starts to increase more and more for the unbinding. And now with our algorithms, this would correspond to a higher friction just simply, and which is, of course, in very good agreement with what the experimentators saw as well in their analysis. And so we concluded that the apparent increase in friction that they saw is not coming from any changes in the free energy of the system, but only that the system is, so that in the data analysis, the analysis does not take into account that there is a hidden parameter, which is the orientation of the protein on the surface so the bound to the surface of the experiment. So just a moment. Okay, good. Because the time is already advanced quite well. So I want to conclude with my presentation here. So I could hope that I could convince you that our dissipation corrected targeted MD simulations approach allows to determine both free energy and friction profiles at the same time from a set of unbinding simulations. And that with temperature boosted Langevin equation simulations, we can then access as well timescales of processes which are beyond the capabilities of molecular dynamics simulations. The major challenge that we face when we want to predict especially unbinding rates of ligands from binding from proteins is that we need to find, first of all, the pathways that the ligands take out of the protein, and B, the crucial collective variables that describe these pathways, and that the respective errors that we do here are based on changes of the fluctuations in the system coming just from the unbinding, and that we need to be aware of that there is a certain error margin that we always face. In case you would like to perform these simulations yourself, here are the respective literature for this. And we just recently published our analysis method as a standalone Python package called DCTMD as well, that you can directly find under GitHub and download there, and which is designed in such a way that you can use it in combination with GROMACS to perform simulations and calculate then free energies, friction factors, and include then our pathway clustering approach, which is called Mosaic, to perform all the respective pathway separation analysis that you need to perform here as well to come up then, or to apply our approaches to your protein or ligand system or condensed matter system of interest as well. Yeah, and with this, I finally conclude my presentation. Thank you for your attention, and I'm looking forward to your questions.
Yeah, thank you very much, Steffen. It's interaction time for everybody, those online and also. So if you're online, please unmute and then you ask questions. And there's a lot in the room. Please feel free to come to the front and you ask if there are any questions or concerns. or if you have any remarks, please feel free and come forward to give your remarks. Okay, while we wait for people to discuss and whether they have questions or not, I would like to take the floor to ask a few questions, if you don't mind.
Yeah, sure.
Okay. So, I'm thinking about the recent developments in this field where AI packages or artificial intelligence or large language models or these big codes are trying to enter into the game of drug discovery, but they are failing quickly. My question about this is that, is it because these AI models are using primitive approaches other than what you've just discussed with us? That's why they are failing? Or what could be the real problem?
Okay.
Yeah.
Okay. Yeah. Okay. There first. Okay. I need to differentiate the answer now into two different points. Okay. So machine learning in this case here is either used for these kinds of quick scoring approaches. So that would be what we describe as in this moment that we describe as relative binding rate prediction. That would be that you essentially just feed experimental data into an AI model and so train them together with the respective unbinding rate that you find for drug target, and in the hope that then in case you just introduce or encode a new compound, that it will give you an estimate of the unbinding and binding rates accordingly. That is one piece. So these are developments which are then called quantitative structure kinetics relationships. I have to say I'm not working on this field. The challenges that I see there is that of course encoding chemical structures into some vector form and the other way around, representing chemical space in a good way that you can train such a model is, of course, depending on how much data you have. And mostly, you never have enough data for a machine learning model. And there are so far few methods where you can really measure kinetics in a reliable way. So this is something that we discussed in a couple of meetings a while ago as well. It is so far not really clear for a lot of these entries in publicly available databases how valid they are. So there are few database entries or sets of protein ligand systems where you have a reliable test, which means that you have measured so that different people have used the same method on different machines to measure the same compound to have an error margin, which is reliable. Second thing, now calculating rates based on physics approaches to obtain absolute rates. Yeah, oh boy. These methods are still using normally unbiasing, so bias simulation, so where you use some methods to accelerate. Usually nowadays, so either people use tau ramped, so that, for example, has been introduced to you by Ariane Nunes Alves. Or the majority of people are using metadynamics. For some different reasons, this is the method that has had the largest traction, which most people are using now. The problem with this is metadynamics still has, due to the problem of following the same kind of physics, has still the pathway problem. And so the hope is that the machine that or the neural network can elucidate or tell you which pathway you take, or take into account that, or find the respective pathway distribution in the system. There's a lot of work by Parinello and others at the moment to build machine learning models for so-called committers. Committers are just essentially a way how to describe the transition pathway, so the transition path positions. It is pretty much, it's another approach to solve the same kind of problem. The problem that I see here is more always that machine learning models face the challenge that you create a machine which gives you some answer to a problem, but you cannot with which not easily understand what the machine is learned. So the so-called, which is the backtracking problem. Okay.
Yeah.
So usually for us here, we are interested in what is then the reaction coordinate which describes us the pathway. So or the other way around, what is the mechanism which is crucial for unbinding of that drug? And we, in a way, get that for free by employing the principal component analysis, because then we just need to take a look into the eigenvectors, or as well for our clustering method. So we can take a look on what these clusters are of trajectories, where they go along, and where do we have still overlap. So because the overlap is found in the off-diagonal elements here, and how strong is this overlap still? Is there some kind of little bit of similarity between the situations there? Okay, so to summarize it, machine learning models are good in case, okay, this is maybe a bit controversial, but machine learning models are good in case that you've got no knowledge about anything in your system.
Okay.
But in case that you really want to later use your knowledge to come up with design rules, for example, in the end, you then for creating a compound which is better suited to unbind slower, it is better that you know what your system learned. And for this, you should better rely on methods or machine learning models or methods where you can invert your algorithm, which would be then, for example, principal component analysis.
Thank you very much. So in summary, I'm thinking that machine learning just comes in as one of the tools in the entire framework of toolboxes that we should use to rationalize the preclinical discovery, methods and how we should approach interpretation of our results. Okay.
Yeah. Maybe if I may very shortly, because I just jumped over this, one additional benefit of the method that we do is that from the side of statistical mechanics, such a friction coefficient and free energy, they are complementary informations with each other, because the friction coefficient represents all the degrees of freedom that I have integrated out to obtain the free energy in a way so that I ignore by calculating the free energy. And so in this case here, that means that the friction coefficient can maybe give me insight into dynamics that I cannot get information from the free energy. Here, this is the case. This is now the case again for the trypsamine benzamidine system. And you see in the bound state here on the very bottom left, the drug sits there a bit like a, well, okay, it's a bit like like a plug in a bathtub, okay? And it's just essentially shielding this binding site, this aspartate here from the surrounding. And the transition state here in red, in blue, in the free energy, position 2, that corresponds to an electrostatic interaction between the ligand and the protein, which is at a maximal strain. So, so where the ligand needs to move against the electrostatic interaction. However, what we then see is this is the transition state, but the free energy, so the peak in friction here at 3, that is not appearing directly at the transition state, but this is appearing directly after, here at the slope. That is where we find our peak in friction. Why is that? What that is that at the same time, when the peak in friction appears, the number of water molecules in the binding site suddenly goes up. And so this is a situation at position 3 where the ligand is far enough out that water can rush into the binding site. And the water, of course, the molecules, they place themselves between the electrostatic interaction, between the positive charge of the ligand and the negative charge of the protein. And by this, it dampens out the electrostatic interaction. So that means the potential energy of interaction goes down on one hand. And on the other side, the ligands, so the water molecules rush into the binding site, of course, bump into the protein and the ligand, and accelerate it, and they exchange as well then kinetic energy. So which means that the system is in a high potential energy state, and then this potential energy is transferred into kinetic energy of the water molecules, and the water molecules then disperse this kinetic energy out. And this is then the dissipation that we need for this high energy state to go into the electric equilibrium of the thermodynamic equilibrium of the bound state as well. And if you remember now from Kramer's equation, the friction in this case is defining as well the unbinding rate to a certain extent beside the binding site. So it turns out that the major contribution here for friction seems to be water molecules. And one of the approaches that one might take now for changing the unbinding rate of the compound would be to play around with either letting more water molecule into the binding site more early, or hinder that influx of water molecules in addition. Okay, and this offers then design options that would not be observable again or understandable in case that we do not have the friction coefficient as in complementation, so as a complementary to the free energy.
So if I understand clearly, so now we have to look at how the dissolution energy of the ligand or whatever drug it is, like how does it vary? Look at the water model, and then how water accesses or interacts at the binding site, right?
The important part is here, it's not, okay, it's not about solvation energy, because energy would be again free energy. It's about solvation dynamics, okay? So as a time-dependent phenomena. Okay, that's the important thing. Please remember, energies are equilibrium statistics, so like stationary properties where we ignore the time, having integrated out. This here, and this is equilibrium statistical mechanics. Here we deal with time-dependent phenomena, and this is therefore not covered by equilibrium statistical mechanics. So this is non-equilibrium statistical mechanics that we need to deal here with.
So in the framework of tools, you don't use. Do you use GROMACS? Do you use GMM-PBSA? Do you use FEP? Like, what is your stack?
In this case, usually what we do is we use GROMACS. On one hand, because it's very efficient from the computational side. On the other side, we need this constraint unbinding. And there are only two programs which really use that or have that included nowadays, which are GROMACS and CHARM. And from these two, GROMACS is I have to say, the more approachable and the more and at the same time the more approachable and distributed program, and on the other side as well, it is performing way better on GPUs. Just
do we have any questions online?
Yeah, I have a question. Sorry.
Yes.
Yeah, so my question is, do you compute like different ensembles of maybe an unstable trajectory and then a stable trajectory, and then you compute for this frictional contribution to the binding, or you just look at because I think that if you have an unstable trajectory of a ligand, you expect maybe the position or the cavity of the ligand to have more water molecules playing around in the pocket of interest, compared to maybe a stable trajectory where the ligand occupies this pocket and then you have limited number of water molecules having something in there. Is it a distribution problem? Is it an issue with maybe computing for the unstable trajectory to be able to determine these differences, and then you end up saying that maybe because of the position of the ligand in the pocket, then the difference is what contributes to whatever you are trying to compute. Do you get me right?
to better understand your question, can you please define me? What do you understand with a stable and what is an unstable trajectory? I don't understand what
Okay,
data could you please describe?
so let's say you have a ligand binding a site. If the
Mm-hmm.
ligand leaves the site and then it goes out of like the ligand binding pocket, and those
Mm-hmm.
pockets are covered by, I mean, at that point, you know that your compound is probably not stable if it leaves the site. Let's say you're computing ligand binding molecular dynamics or something.
Mm-hmm.
And then I am assuming that within that pocket, then you have more water molecules occupying that site if the ligand is not present. That's like
Mm-hmm.
an assumption I'm making, unless I'm not getting it right. So
I. Mhm.
looking at this frictional the hydration shell water and then the frictional computation that we are doing now, are we looking at two different parts of a simulation where we know that the maybe the number of like water molecules occupying the pocket are way higher in an unstable trajectory as I have defined compared to a stable
Mhm.
trajectory? Are we looking at the difference to make meanings out of our simulation, or is just even in the presence of the ligand?
Okay. Now, okay. So the situation there is that we do not make a difference between this kind of this definition of a stable or unstable trajectory. Okay.
Mhm.
However, um, we this is something that we're just working on right at the moment, which we found to heavily impact our simulations. Um, we need to start with a situation, our simulation. So we need always, I mean, first of all, we need to start our simulation from a well equilibrated structure, protein structure. And we are very much dependent on the water molecules in the simulation being at good positions. That means if we have too few or too many water molecules, the free energy that in the binding site, for whatever reasons, bad preparation of the system, or just taking the wrong simulation snapshot, um, we will get significantly different free energies. Um, and this is something that we're currently working on how to do that better. It is well, yeah, it's a general problem for our approach. However, it turns right at the moment. Okay, we're working with some other people together, and these are very preliminary predictions, but it might be that this is a general problem. Okay, so that we are even more sensitive to good starting structures than free energy calculation simulation people would be. Did I answer your question?
Yeah, I mean, I understand to a point, but I'm also thinking that if even if you equilibrate your system well, it
Hmm.
doesn't it doesn't necessarily guarantee that it's probably going to be completely inside the pocket during your simulation time. It's definitely going to be if there's like an entropical contribution somewhere, there's like a competition or with water molecules somewhere. It can be that in the middle of the trajectory, there will be so much water molecule going into the side that will compute that will
Aaron,
compete with
can
the
I come in?
yeah.
So the point here is now, Stefan is trying to ask whether there is a metastable state of a protein ligand complex when you
Mhm.
do your initial simulation, where the ligand molecule does not, dissociate from the binding pocket. In this case, we think about a K on, K off. So it does not dissociate. Where do you expect this metastable state? And by metastable state, from a molecular docking perspective, so you are moving from molecular docking where you have artificially, investigated how the ligand binds perfectly with the protein, and then you put it in water and simulate it over a long period of time, maybe 1 microsecond, and the ligand does not leave the binding pocket. This is what he's trying to say is a stable trajectory. But Aaron, the discussion here has to also do with the principle of trying to understand the unbinding pathways of a ligand so that we can understand the unbinding kinetics of this protein ligand complex in order to rationalize, the pharmacokinetics and pharmacodynamics of drugs. So I don't know if I was able to convince
Oh, I understand.
about the
I
subject.
understand. So are we talking about the unbinding state after binding or just before binding?
So we are trying to incorporate the unbinding kinetics, which is mostly neglected. I think Stefan can take it from here, because if you have to look at how it unbinds, you have to apply some external force, which in this case is the friction, the pulling force. Let me put it that way.
Okay.
But Stefan, you can take it.
Yeah. The problem is exactly. So the compounds that we investigate, they never unbind in the framework of an MD simulation, or where you do not employ any kind of acceleration. They just simply sit there because we cannot simulate the timescales which would be necessary to observe this. I have to add with this. I'm currently taking a look into some molecular fragments simulation, so between a small protein and there's some kind of pre-drugs, so compounds that do not bind very tightly there, to see how. So when with the hope that I can see some binding and rebinding effects appearing. That I do investigate as well, but this is a completely different question. And I will use this more as a benchmarking tool for this approach here, because this is definitely necessary. But it comes with other problems that I currently don't want to talk about, because I did not check everything there yet, and B, that would be another complete presentation actually.
All right, thank you.
So another question is, why Langevin dynamics?
Oh, because they are super simple. In the end, I mean, so of course, we do make some significant, so like very crude approximations here, okay? Which is okay. So first one is that we can write down this Markovian-Langevin equation. That is already a stretch, because we have this drift term here, which depends on the free energy, and this is normally not what you have in a Langevin equation. Usually, you have here something like a potential, which is there, not a potential of mean force. Second part is Gaussian noise, or white noise, which is delta distributed. This is something that does not exist in nature. Okay, so naturally we always have white noise. Why do we do this still? Okay, simple. Because then we only need to parameterize two properties, which is very quick. And the numerical solution of that equation down here, sorry, a moment. So the numerical integration of that equation down here, you could do in Excel, in case you would want that. Okay?
That's right.
Yeah. And so this is super, super, super fast. And please remember, the problem that we're facing here is if we want to go to long time scales, with molecular dynamic simulations, there are two things that we need to tackle. Which is that we need to calculate, so we need to throw away as many computationally expensive steps as possible. One thing is, here we need to calculate all the forces, pairwise forces in the simulation system. That would be, even for a small system, you're very quickly in the range of millions of equations per time step. Second problem. What? Come on. So second problem, when you have that, even if you throw away these time steps, you still need to make all the calculations, each solutions stepwise, sequentially. So you cannot paralyze the just calculating this time series here, this loop. You need to run that sequentially, and that needs to be done very quickly. And you want to do this in such a way that you need to reduce the amount of particles of this Q. That vector needs to have a very small size. If you have millions of atoms, that will be millions of numbers. And this one here, just a moment. Sorry, throw that away. That equation down here, again, this is two numbers which you plug in. That's it. And so it makes a lot of crude assumptions, but still, given that these crude assumptions, we are on par with the accuracy of other prediction methods, which are on the market as well. So for example, with intracurrent matter dynamics. So that means we make errors, but it seems that the errors so far are small enough that we can live with that.
So another question is, how do you come up with the data sets that you use to train a model and etc. from one
Oh
of
yeah,
us?
well, okay. I mean, this is just again, moment. That means just brute force simulations. So that we do these kind of simulations in GROMACS, and we just do them over and over again. Unbinding usually that takes so one trajectory we can pull out a ligand usually within depends on what kind of velocity we pull. That takes usually something like between 3 and 30 nanoseconds per run. Okay, and we need again per pathway 100 runs. So in case we are really unlucky, we need to perform something like, well, 200 to 400 simulations.
Whoa.
Yeah.
So like, what's the length of each of these 400, 200?
Yeah. Again, so it depends on the velocity that you use. It's between 3 and 30 nanoseconds. That means technically, in case your cluster is empty, you can do this over a weekend.
Okay, fantastic. But looking at your approach, you seem to be rewriting the rules. So how will that affect the drug discovery timeline, if we think about it? If we adopt this into
Okay. I need to make the disclaimer that here this is very much still foundational research. Okay, so we are trying to come up with the methods that people can use for predicting rates. Okay, because the problem in the end, what you need to do is at the end, when it comes to this here, or let's make that here. In case you're able to then predict the rate for a compound, you need to convince a chemist to synthesize that. Okay. First of all, second thing is for a drug company. This is a so for them. This is the question: what is cheaper? Is it cheaper to take somebody who just can produce these compounds experimentally within a short time, or is it cheaper that you run your simulations and you choose you pick a couple of these compounds before? And for this next thing, so we use a lot of open source software in an academic framework. This is not necessarily what you have in industrial framework as well. There, people usually are working with dedicated program packages like Schrödinger, where you have like pipelines that can be quickly programmed and implemented. Schrödinger right now, since a year, for a year roughly, has now implemented tau rammed and as well metadynamics. So it is there now that people could use that. Now what we still need is to find a case where somebody steps up and shows that what is that this kind of designing is feasible, and how much work is that, and what does it need to be successful, and how much work is that, and how much money does that cost?
Okay.
So it is a possibility to improve this or to improve this conundrum here that I showed in the beginning, but we are at the very beginning of that. Or let's say not at the very beginning, but we are at a crucial point where we need to show that this is actually possible.
All right. You have more questions? Yes. No, ask. Okay. So Esther will send you an email. She has another question, but in the interest of time,
Okay,
she sent an email.
Okay, all right, we could do that.
Yeah. Okay, thank you very much, Professor Steffen Wolf, and thank you so much to our participants online, and also to you for coming for today's webinar.
Thank you, it was a pleasure.
Yeah, we'll upload this on our YouTube platform, so please watch out for it. Thank you.
Okay, thank you.